everyone, how's it going? And welcome to the Community Conversations. My name is Liz, and I am from the growth team at Dfinity. Community Conversations is an opportunity to discuss technical developments in the ecosystem with the community itself. Today, we have our very own Andreas Rossberg, co-creator of WebAssembly and principal engineer at Dfinity. Andreas will be giving a talk on the Motoko programming language. Motoko is designed to directly support the programming model of the internet computer, making it easier to efficiently build applications and take advantage of some of the more unusual features of the platform. So please give Andreas a very warm welcome. And Andreas, without further ado, feel free to take it away.
Yeah, thanks, Liz. You already stole my first slide, I guess. Okay, let's share and get started. Okay, yeah, so I'm gonna talk about Motoko, and I assume most of the folks who are here, who joined in here, know what Motoko is, but of course, I have to do that intro anyway. So what is Motoko? It's a new programming language we developed, and it's designed especially for both WebAssembly and specifically for running WebAssembly on the internet computer. We started development in 2018, like 3.5 years ago almost. And I think we first revealed it 2 years ago, roughly. And it has been open source. So first the library was open sourced last year, and earlier this year we open sourced the compiler as well, and both is under Apache license, and you can find it on GitHub. And open issues, do pull requests even if you want, if you dare, all that thing. Okay, so I'm saying here it's designed for WebAssembly. So maybe I should briefly talk about WebAssembly, one single slide. So what is WebAssembly, or also called WASM usually, because that's shorter and because the whole name WebAssembly is a misnomer anyway. So probably also most of you are familiar with that. So WebAssembly is like a new code format, a low-level code format that is designed to have all these nice properties, being portable, being safe, being efficient, but also interestingly for our domain, it's like well specified actually, and it has a deterministic semantics, mostly deterministic anyway. And I just see a typo there. And what is interesting about WebAssembly, it's kind of like a virtual machine essentially, but it's a low-level virtual machine. So unlike other like popular virtual machine technologies that you probably are familiar with, it takes a bit of a different route. It abstracts the hardware, so it's like a virtual CPU. It's not an abstraction of a specific programming language or programming paradigm. So it kind of like abstracts from below, not from above. And the other thing that is special about WebAssembly is that it actually has a very rigorous mathematical specification, which is part of the standard, and includes a machine-verified proof of soundness, or actually several proofs have been done with different theorem provers. So it's not just some random thought-up technology, it's actually having a very rigorous technical and formal basis. It's an open standard. It's developed under the roof of the W3C because it started out as a web technology, but it has always been from the get-go designed to be like universally applicable. So not just to the web, but to any other kind of environment as well. And there are many of those where it has been applied. So besides the web, it's being used in cloud computing and edge computing, in mobile, and there are applications in IoT, embedded system, even desktop. And of course, there's the internet computer, which also runs it, and which is why we are all here, right? So just to give you that as a background, so this is like, as I said, it's an abstraction over the hardware. It's like the core of the programming model of the internet computer. And by its very nature, you could, in principle, program it in with any programming language you want. So any language that has a compiler compiling to WebAssembly and supporting the environments or the environment that the internet computer provides could in principle be used to program it. So in the next few slides, let me just give you a big sort of like overview of Motoko, like from a bird eyes view. What are the design essentials here? So first of all, why do we even do it, right? So as I just said, you can actually program WebAssembly in any language, at least in principle. So why did we invent a new programming language? And that is a very fair question, and a question that is asked a lot, because actually developing a programming language is a huge endeavor. It is easily underestimated how much work it is. I mean, there's the compiler, but that is actually the smallest part of the work. You have to create an entire ecosystem to make it useful, right? And I wouldn't even claim that with Motoko we have already traveled the entire way there. There's still lots of work to do. And besides being a lot of work, it's also the case that there are lots of languages invented out there. Like many of them are hobby projects or half serious things, but the fact is, like, even with the more serious ones, like almost all of them never reach critical mass. And that, interestingly, is mostly independent of their actual technical merits. There are lots of other factors that factor in there. And so you really need to make a language successful. You need a lot of, there are a lot of premises you need to meet. So you need to actually have the right motivation. Why does the world need another language? Why does the world need this particular language? And many languages you see out there are like kind of like just variations on the same scheme, so on the same theme. So it bears the question, why do we need all of them? So you need to design it right. You also need to time it right. So you might have a beautiful language, but it might be ahead of its time, or maybe it's coming way too late because the train has already left the station. And interestingly, actually, that at least that's my experience, to make a language successful, it needs to have a niche where it's actually useful, more useful than any of the existing competition. And then there are all the usual things, like you need to do the right marketing, you need to have sufficient resources because it's a lot of work, right? And of course, you also need quite a bit of luck because there are so many like non-technical factors and social factors that you have no control over. Anyway, for Motoko, we believe that we have all of this, or we hope. And this is kind of what I'm going to talk about. So just like as a heads up, the talk I'm giving here will not be very like detailed or technical. It's more like a very high level talk about Motoko, why we have it, what is the design philosophy. I will give a few simple examples, but nothing like that goes into the weeds. So I hope that you saw Jan's talk the other week, where he showed more like how you actually code with this. So this is not what I'm going to do here. So why did we do Motoko specifically? Well, there are mainly two reasons. One is that the internet computer is kind of like a fairly unique platform. It's new, and it has a very unique set of features, and it is a very unique environment. Like, you don't have the usual operating system that you can access. So a lot of things that usual languages built upon and their implementations and runtime systems and so on is not available. And of course, we also want to provide nice support for the nice features of, or the unique features of the internet computer. So we want a language that allows you to seamlessly use that in the most elegant fashion we can think of, and not have it feel like an afterthought. The other reason was that, at least at the time we started, WebAssembly and the whole ecosystem was still like dominated by low-level languages. So at the time, there were basically only two mature compilers for WebAssembly. That was C++ and Rust. And while these are like nice languages in their specific niches, they are, as I say, they are very low level, and a low level language doesn't seem like a particularly good match for writing things like smart contracts, because they tend to be unsafe and other disadvantages. And so the goals here was that we wanted a language that is designed to be productive, and because of our application domain, also put a particular focus on minimizing errors, because errors can be fatal in this domain, right? And we wanted to take advantage of the novel features that the platform provides. So Right. And the last point is also important in comparison to other languages on other blockchains. We kind of wanted a language that is more like conventional in the sense that you don't actually need to know anything about blockchains, right? The blockchain is an implementation detail that should not surface in your developer experience. It should be irrelevant as much as possible. So what are the design goals? What's the philosophy behind Motoko? Well, there are kind of 4 pillars here. One is, of course, and I mean, most of them are not surprising, and probably all languages claim that, but let me talk through them anyway. So one, of course, is we want to provide a productive tool for developers, right? And that means that you want to be able to focus on the essentials and avoid distractions by your stuff that should just not matter, right? So that's why you want a high-level language where you don't have to pay attention to irrelevant details like, say, memory management or all these things. You really want to focus on your business logic. I actually hate that word, but I guess everybody knows what it means. Another thing that's maybe more specific to Motoko in a way is that we wanted it to be accessible. And by that, I mean that like common developers who are familiar with mainstream technologies can just use it without too much effort. So it ought to be comparably simple, and it ought to have a look and feel that is familiar to many folks. And of course, there's always there are always conflicting goals here, and you have to trade that off to some extent with other goals. But to the extent possible, it should be familiar and simple. Very important here, of course, is also that it's safe. I mean, this is kind of standard nowadays, at least in high-level languages, but it can mean many things. But of course, it means that like programming errors should never be fatal in the sense that your program crashes or misbehaves in completely unpredictable manners. So when there is a fatal error, it should be detected by the language and the runtime and be properly confined. And then relevant in kind of the smart contract domain in particular, you really want a language that helps you writing a correct program, right? So there are application domains where this is less of a concern. So for example, when you're writing front ends on the web, I mean, JavaScript is a terrible language to write for writing correct programs, but it doesn't really matter, right? It's like, if there's a glitch in the UI, who cares? But for backend stuff and smart contracts in particular, if they're like dealing with I don't know, funds of value, that is fatal, right? And we have seen in the past on other systems that these can be attacked, and if the language has questionable features, then that can be an attack vector. So for Motoko, we really try hard to design it such a way that it avoids error-prone features and footguns altogether, or where you can't avoid them, you at least want to make the default be the safer alternative, right? So for example, if you have a choice between defaulting declarations to being immutable or mutable, you pick immutable because that's safer. You pick private as the default. You pick, you want types by default not to be able to contain null, right? So if you want to allow null, you have to be explicit about it, and so on and so forth. So static checking over dynamic checking, all these things. And if you want something else, you should really be explicit about it so that it's clear from the program that you clearly have thought about it. The reader can tell that you picked this consciously, and so on. And the idea here is that you really want to prevent a whole class of errors by construction. So by designing a language appropriately, there are certain things that simply can't happen. So how did we achieve these goals? So with Motoko, well, various things. Okay, so in terms of productivity, one important thing was that we wanted to have direct integration of like some of the main concepts of the internet computer. So like canisters, for example. So canisters surface as actors in Motoko, and I'm going to talk about that a bit more later. So it has direct integration with Candid, our interface definition language. it has features which are somewhat more common nowadays, like async await. It obviously has garbage collection, so automatic memory management, so you don't have to worry about that. Stable variables, I also going to say something about, and then things like quality of life features, like some form of type inference, generics, and pattern matching for writing concise and readable code. In terms of accessibility or like familiarity, well, that kind of like gives you no choice these days than to pick like standard curly braces and semicolons and angle brackets syntax. So that's what we did for Motoko as well. And you want to have some form of classes and objects because that's what many people are familiar with. And with actors, we try to kind of piggyback on that familiarity of the object concept and try to make them as similar to objects as possible. The type system is relatively simple, and we really try to avoid introducing fancy terminology. So there are quite some fancy concepts in Motoko, but we try not to call them monad or something like that. And yeah, safety is just the usual thing. You have garbage collection, you have a type system that is actually sound, so you can actually guarantee that certain things can't happen, unlike other so-called type systems that have glaring holes in them. And then you have the usual things you need for memory safe language, like array access is checked and so on. And in terms of supporting writing more correct code, well, the actor system, the actor model is an important part of that. I'll talk about that. And the type system is also relevant, and it has a fairly modern, rich structure where you have things like records and variant types, and which allow you to encode and compose more complex things. One important thing, for example, is that the default number types are unbounded, so infinite precision. So things like integer overflow can't happen, right? You also have a choice of a number type that is bounded, but in that case, you at least get an exception if it tries to overflow. So certain like wraparound errors that were the cause of some attacks on other blockchains can't happen in Motoko. And in general, the entire semantics tries to be very high level, right? So avoid low level foot guns and things like that. Null types are explicit. I already mentioned that you can't have uninitialized variables, and there are various other small things like small design choices which always try to err on the side of avoiding error-prone behavior. So really overall, I mean, like the larger part of the team are all ex-researchers in programming language implementation and theory and practice. So we really try to apply all the lessons learned in decades of research and practice to Motoko, and not repeat the same old mistakes that shouldn't have happened, like should have been learned 30 years or 40 years ago already, but still keep being made, like starting a language without a proper scope system, for example, scoping model for variables. It's amazing how much is really bogus in mainstream languages. Okay, so that was kind of like the overview of the general philosophy, and for the rest, I kind of want to walk through the 3 or 4 main concepts which are more specific to Motoko and its role of running on the internet computer. So the first one I already mentioned is a couple of times, is the actor model. So I don't know how many were familiar with that model before. It's actually quite an old idea. It's a model for concurrent computation, first of all. And it was invented back in the 70s, but at that time was more like an academic concept. But in more recent years, like maybe the last 1.5 decades, it has seen more uptake in different environments. And what is an actor? So essentially an actor is kind of like an object. So like an object, it has methods and private state. But the main difference being that method invocations, so message sends, are always asynchronous. So you cannot synchronously call into another actor. You can only send an asynchronous message. And on top of that, when an actor receives such a message and a method executes, then this is an atomic execution. So only one method can execute at a time. So like in Java terms, all methods are synchronized implicitly, right? That is a fundamental property of the model. So in every actor, only one method at a time can execute. And that is done by actually giving them an implicit message queue. So if there are other messages that arrive while one still executes, it's simply put in the queue and will run after the current one. Yet it's immediately the message. So for the sender of the message, so the caller, that just immediately sends the message and proceeds. Its execution will not block, right? There is no blocking whatsoever in the actor model, and that's another important property. Because what these properties give you is that it's actually two important things. So it prevents race conditions because everything is atomic by construction. There can't be any race conditions. So you always have synchronized access. And there can't be any deadlocks either because there's no blocking, right? You can still, of course, write bogus protocols of communication where some actor is forever waiting for a reply, but it's not blocked at the time. It can still execute other stuff. So that makes it a great model for concurrent programming, and that's why there has been more interest in it recently. It's also a great model for distributed programming, which is kind of like an extension of concurrent, if you want, because the asynchronous nature of message sends is kind of a very natural fit for the latency that you naturally have in a distributed system, right? And why is that relevant for the internet computer? Well, actually, the internet computer is a distributed system if you look at it from the right angle, because it has subnets which run separately and independently, more or less, but can communicate with each other. They're basically separate processes, if you want, or nodes in a way, right? And virtual nodes. And there's unpredictable latency for messages going between different subnets. But even on the same subnets, you can't really predict how long it takes for a message to be received. And so it's also no coincidence that the canister model that is the primitive on the internet computer is essentially just an actor model. So it's really just, we invented a fancy new term for it, but it's really more or less a variation of the actor model. And Motoko now surfaces it as that directly. So how do actors look in Motoko? To give you an idea of like how symmetric they are to objects, let me start with a simple object. So this is like probably one of the simplest objects you can think of. It's like a stupid example, but it fits on a slide. It's just an object that encapsulates a counter. So you can get its current value and you can increment it by some delta. So for example, and this is like a singleton object, right? So there's just one counter object. So you can increment it by 3, say, and then you can read the value and maybe add 1 to it, for example. And an actor version of this would look almost exactly the same. There are only a couple of differences. So first of all, we're using the actor keyword here instead of object. And second, the result of the get message has to be an async value. And I will go into what that means in a bit more detail later, but yeah, so this is the result of an asynchronous communication. Other than that, it looks exactly the same as the object. So this is like a singleton actor. And you can use it also in almost the same way. The only difference here now being that, well, because the result is asynchronous, you actually have to await it before you can add 1 to it. So what get returns is not a natural number, but it's an asynchronous natural number. And then the other thing you usually have in object-oriented language is classes, right? So here's how that would look in Motoko. I can turn the counter into a class, and it has a constructor argument in it with which I start the state. And then I can create like a new instance of that and do something with it. And again, you can do exactly the same with actors in Motoko. So there's this notion of an actor class. So that is the actor version of a class. So again, the differences here are really minor. So you have to put the actor keyword in front. You again have the async result. And that's it. And then you use it similar to before. You have to await the result of the get, like above. But interestingly, also, you have to await the constructor call, because for actors, construction also is asynchronous. And that is actually a consequence of how the internet computer works, because an actor ultimately is a canister, and a canister cannot be created synchronously. Right, and yeah, so that's what I just said, right? So what are actors in terms of the internet computer? Well, an actor has a one-to-one correspondence to a canister. It really is compiled into a canister. Every actor is a canister. And invoking a method on an actor is then a cross-canister message, right? And you get a reply there as well. And the arguments and results to such a call are automatically serialized and deserialized as candid values. So that's one of the nice productivity features of Motoko, that this is built into the compiler. It understands candid and just does all the work for you. So it will send along some values here as candid, but you don't really have to worry about it or do anything manually. And the other interesting thing is that if you instantiate an actor class, what that means is you're actually dynamically creating a new canister. So this allows you to programmatically create canisters from a Motoko program. So one thing you already saw in here is like this use of async. And that is another important concept in here, which goes by various names, one being futures, one in slightly different communities is promises, and there are also communities that use both terms with different meanings. Let me go by futures because that's kind of the most coherent way of calling them. So what is a future? Well, a future is a placeholder for a value that you don't have yet, that will become available somewhat later. Again, this is actually a very old idea. It also originates from the 70s, from the functional programming community. But it only became popular really over the last decade in mainstream languages. And in most of these languages, and in Motoko as well, a future represents the result of an asynchronous computation. So in Motoko, a future is represented by the type async t. So that's the type of a future with a value, the future for a value of type t. And such a future cannot be accessed directly, so you can't get the value out directly. You have to await it. And that was the await construct you already saw. You have to explicitly await it. And the whole upshot of that is that you can write programs with asynchronous like computation patterns in what is called direct style. So you could write them as if they were synchronous. You just sprinkle in the right awaits in the right places, and then it just looks like an ordinary program. And you don't need any callbacks or anything like that, like in JavaScript. That used to be the case, and it sometimes was called the callback pile of doom or something like that. Anyway, you have all these nested callbacks, and that really is not a very scalable approach to programming manually. And when you have async, basically the compiler does all the work for you. It does this so-called continuation passing style transformation, transforming your program implicitly into this kind of callback stack, but you don't have to write it. So in Motoko, you already saw like futures being kind of implicit in this program, in this simple actor before. So this async net is a future type. It's the future over natural numbers. And a future is actually created by something we call an async expression. So this is the method here is actually just a composition of several features of a function in async expression. So you can use async expressions as a standalone thing. So for example, here I have an async expression that does some computation asynchronously, like by adding 42 to the result of calling this method on the actor. And because I'm inside an async computation here, I can do await. So I can only do await inside other asynchronous computations. But this entire thing is again an asynchronous computation. So when I evaluate this, I immediately get back a future. So X has this type async net before the computation even starts. So the computation here, the program will continue, and then at some later point, this thing will be executed. And I can compose these in various ways. So for example, I could have very stupid example here, like a function that just increments this counter using like the result of combining several values acquired from other computations. And again, like the body here essentially is one of these async expressions. So really, this is just a kind of syntactic sugar, if you want, for a function whose body is an async, who returns a future. So there's no primitive notion of an async function. It's really two separate features combined. Another important feature of the internet computer is its orthogonal persistence. So the memory of every canister and thereby every actor in Motoko is implicitly persisted. Conceptually forever, right? So if you install an actor onto the network, it will have some internal state, and this state will just live on forever, at least conceptually, right? As long as the actor is live and it's not taken down explicitly. So yeah, this is implemented by the internet computer itself, and what it does is, in terms of WebAssembly, it just remembers the memory of all the modules in your WebAssembly program, as well as the tables and globals that are defined in there. So this is an implementation detail of the IC, which the Motoko runtime doesn't have to worry about. But so this all works. This all works fine as long as you have your actor and it just runs and runs and runs, and you don't need to change it. Where this whole notion of orthogonal persistence becomes tricky, though, is when you want to change the actor, when you want to upgrade the code. Because then you have the problem that, you know, this might change the form of the internal state of that actor, right? So there can be many sources of that affect how the internal state is represented. So for example, the most obvious one is you change the program, your own source code, or more indirectly, you use different versions of some of the libraries you're depending on. It could also be that you're using a new compiler version that maybe has changed something about its memory management or something. So we don't want to like preclude that forever and being stuck forever with one fixed like heap representation. That would be very inflexible. So new runtime versions, you might also be using tools in your toolchain to generate some of the code, and they might change in some subtle ways. So when you rebuild, even if you rebuild the exact same program, if some of the kind of dependencies have changed, you might already have a different binary in the end, a different WebAssembly program, which might not allow to reinterpret correctly the like internal layout of the memory that was saved from the old version. So how do we get around that? Well, we require you to be a bit more explicit. So a programmer in Motoko can mark a variable in an actor, which is part of the state of the actor, as stable, but they have to do so explicitly. But when they do, they get the guarantee that the value of this variable will actually survive any upgrade. And there's a trade-off here. So by doing so, you also accept that the type of the variable is restricted. So first of all, it can't really be changed in an upgrade because the value has to be still valid for the new version. So you can do a minor change. It can become a super type, but other than that, it can't change. But more relevantly, also the set of types you can use for stable variables is also restricted. It's restricted to kind of the same kind of values that you can use in message sense. So values that have a self-contained representation, essentially, that doesn't depend on anything in the code of the program. And that means, for example, that functions are not allowed in stable variables. And as a consequence, also objects are not allowed in a stable variable because they indirectly refer to functions. So there are some restrictions on stable variables, and you have to make the right choice. You have to think about whether you are fine with these restrictions and make this variable stable, which gives you survivability of upgrades, or you want to have maybe a more efficient representation or something like that, and then you have to do more manual work during an upgrade. So you can work around the stable thing by or you can have non-stable variables and still survive upgrades by having explicit pre and post upgrade processing that you can define, but that is a bit less like convenient, obviously. So yeah, in Motoko, like this is the counter example again. I apologize for always using this boring example, but here now I have made the variable stable. And let's assume I use this version of the actor a couple of times. I invoke it with some methods here, some messages, send it some messages here, and I'm using Motoko pseudocode to kind of indicate that. And so I increment it, and in the end, if I look at the counter, I would see 4, right? But now the next time I want to kind of upgrade my actor, I want to extend the functionality of this counter thing. So for example, by adding a reset method. That's the most obvious change here, but there are there's another interesting change to the interface, which is that I generalized the delta for the increment method from nat to int. So it could now be negative. And for that to work, I also have to generalize the type of the internal state. So here, in the original version, the Motoko compiler would have inferred that it's nat, but now I make it int because it can now become negative. Well, and to adjust for that, I now have to kind of change the implementation of the get method because that still promises to deliver a nat, and I could not change that to int because that would be an backwards incompatible change, right? Because there might be existing clients that expect a nat, so if they suddenly see an int, they would break. So I would not be allowed to change that to int. But if I wanted to have that, I would have to introduce another get method that returns an int. But in any case, I can now use this counter, this new version again. So assume I upgrade the counter with this new version, and if I run that, the original state here of that variable n would still be maintained. So because it's stable, it will be preserved. It will not be reinitialized with 0 here. Instead, the old value, which was 4 at that point, will be preserved. And then I get 2 here after I deduct 2 from it. And the last thing, I think I have to hurry up a little bit, I want to talk about is the Candid integration. That's the last important kind of bit. So Candid is like the official interface description language of the internet computer. And it allows you to define multiple canisters, actors, and have them interoperate in a defined way, right? And these canisters can be written in arbitrary languages. So Candid is language agnostic and is designed to work for like any language. It doesn't make assumptions about what the canisters are written in. And it basically allows you to define an interface with functions, and these functions can operate on data, and this data can be composed from various things like simple numbers, but also more complex things like records, variants, and vectors. And it even allows you to put in like higher order things like function reference to functions, or even entire canisters, which are called services in the Candid syntax. And the interesting thing it gives you on top of that is that it defines a notion of backwards compatibility between interfaces. It precisely defines that, it makes it checkable. So when you have something like DFX, you can actually have it check that the new interface of the actor, when you upgrade, is compatible with the old one, meaning that it won't break any existing clients. And there is some intention of actually enforcing that in the future. or at least by default enforcing that. And Motoko now like has Candid integration, meaning that it first of all automatically does all this deserialization for messaging. I already said that, but it also allows you to use Candid interface descriptions directly. So you can import and export that, and as a form of like interaction with other languages if you want. So for example, the export is like if I have again the boring code here in Motoko, then the compiler can actually automatically generate a Candid interface for that. So in this case, it would be very simple, but it can do that with any actor you define in Motoko. More interestingly, you can also import a Candid. So if you have a Candid file that describes some canister that is maybe already live on the internet computer, then you can import that. So there are these import statements. So I could import the counter. Let's assume it has this address on the IC. And somehow I have made available the Candid description I showed on the last file to the compiler. So you can either do that by some manual compiler flags, or when you have UseDFX with a manifest, you can configure it in the right way so that it finds it. And now you can just use this as if it was a thing you defined locally. So you could have another client being defined here, which does some function and that just calls into this counter. Although you don't have the source code here and you don't even know or care whether it's written in Motoko, right? So this allows Motoko to like play nice with the whole ecosystem of the internet computer, including other languages. So that was mostly the 3-4 things I wanted to talk about. Let me briefly go through like some of the future directions we want to take. So of course, Motoko is far from done. I mean, the language is never done, but there are some obvious things we want to do. Without enumerating all of them here, maybe just the most important parts. One of the things we're really working on hard right now is improving the garbage collector. So we really want like an efficient incremental collector ultimately, which always does predictable small steps after like at defined points in time. So you don't have these like peaks or spikes in the use of cycles when you do a major collection. There are various feature gaps and quality of life improvements we want to do. There are also some improvements to the type system that we want to do for even more safety, like for example, in the context of async, so that you don't have state dependencies over across and await, things like that. There are obvious things you miss in the library. And then there is the whole thing, of course, with the internet computer having various features and evolving as well. And we already, like, there are already a number of features that the IC provides that you can't directly use from Motoko. So we need to keep up with that. And tooling, of course, there are various things we want to do, and there's never enough documentation either. Right? So just to give you a kind of general idea of what our focus is for the future. Yeah, that is basically what I wanted to say in this forum. This is a summary slide, I don't know. And I think with that, we can go to the Q&A.
Awesome. Thank you so much, Andreas, for that. Everyone in the audience greatly appreciates your time, and we have a ton of questions for you today. So first of all, I think you touched upon this in your presentation, but I think it bears repeating as well. So why should somebody starting out with Canister development choose Motoko over Rust? Because Rust has way more libraries published, more documentation, more tooling. And apparently it was voted as most loved language for the last 5 years on Stack Overflow. I actually didn't know that.
Yeah, well, there's always hype around certain languages, and Rust is certainly a very interesting language. But so personally, I think it has its uses on the internet computer. But as I said, it's a low-level language. It's really a systems language, right? So you want to use it when you really care about the last bit of performance, maybe, and having more control over things like memory management. But I would think that for most applications, typical applications on the IC, like if you think about things like smart contracts, then it's really not a great fit, because you have to care about all these low-level details that like why, right? Like, why would you bother with that? You want something that is more productive and high level. And of course, you can get fairly productive with Rust as well. But I would argue that ultimately you're more productive with a more high level language, which has more nicer integration with the IC as well, right? That would be the other big advantage of Matoko.
Cool. Thank you, Andreas. So next question, are there any plans for abstracting things like long-running processes so that devs don't have to think about blockchains? Because currently any kind of significant file manipulation hits the cycle limit very quickly.
Yeah, so this is something we of course keep discussing, but this is something that will probably rather be addressed on the IC level itself. So when basically what is being discussed as a future extension to the internet computer is that you have preemption. So basically a computation can flow over into the next block or something like that, right? And then that would make it more or less transparent for a Motoko program as well, or any other programming language that you run on the internet computer. We haven't really discussed like any special solution in Motoko itself. Maybe that would be possible, but I'd rather have like a universal solution to this problem than hacking something into the language, because it doesn't just affect Motoko, it affects the entire ecosystem, obviously.
Yeah, no, definitely. Cool. So Andreas, next question. Doesn't including garbage collection reduce performance as compared to other languages like Rust or C++? Couldn't Matoko have implemented concepts like borrowing and lifetimes like in Rust? I think we have some Rust appreciation people in the crowd.
Yeah, no, it's a fair question. So first of all, it's a common misconception that garbage collection is necessarily slower, like especially if you compare it to things like reference counting, which is the only somewhat comparable solution for the more general case. It's actually more efficient in many cases. And if you have an incremental collector, which is what we want to get to, then it's probably universally better than reference counting. Of course, you can use an ownership type system, but that is kind of much more like tricky to work with, and it puts you into this place I mentioned earlier, that you now have to worry about all this, right? Like you have to worry about ownership, which is kind of like worrying about memory management. It's kind of like abstracted somewhat, but you still have to put a lot of thought into things that you shouldn't really need to think about. At least not in many cases. I mean, there are definitely cases where you want to think carefully about these things. And if you're building certain applications, that might matter. But for simple applications, at least I would argue that it doesn't matter. And for like maybe 90% of your code.
Great. Thank you, Andreas. So next question. Does Motoko's actor model provide advantages in concurrency or otherwise relative to smart contracts found in Ethereum?
So Ethereum has only synchronous calls, right? And so all the call chains in Ethereum are synchronous calls, which of course is nice in terms of a simpler programming model. So it's just like ordinary function calls if you want, but it has pretty poor scalability properties, right? The reason we have messaging on the internet computer, and Motoko just really inherits that, is that it scales better if you have things like subnets or something where you have these latency issues, right? So that's what I mentioned earlier, that actors are a great model for distributed computation because there is latency. There is going to be latency, and you should not be blocking on these communications. So the actor model kind of forces you to program in a way that you don't block. And this is important to be transparent about these latencies in your program, that you don't construct it in a way that doesn't scale. So it's more like a necessity of being scalable than like a advantage per se, I would say. It's more like, okay, we are concurrent, we are distributed. What is the best programming model that fits that?
Definitely. Thank you, Andreas. So we had a couple of questions around the same topic, so I will combine them. So what are the plans for Difiny Foundation or the broader internet computer ecosystem to improve tooling around Motoko, like libraries, auto completions, and so on and so forth? Will we ever have some kind of educational resource which walks us through Motoko, for example, from basic concepts to advanced concepts?
Yeah, I think most of these I listed on my future direction slide. So obviously we want to have all that, but of course we are only that many people and can only do that many things at a time. For some of these things, it would also be great. I mean, that's part of the reason we open sourced, right? That we could have community contributions. So libraries is an obvious example, but also documentation maybe or tooling. There are things where we could benefit from the community helping out. And ultimately, an ecosystem is only alive if there is a lively community. Not everything we will ever be able to do ourselves. But yeah, so some of these things we actually want to work on and have concrete plans, and others, well, we want to do them, but we don't know when we have the resource or time to focus on them. Help is always welcome.
Definitely. And I feel like the best educational resources will come from the community ultimately. Like, for example, we have a guy tuning into this call right now who's created something called Matoko School, and he creates educational resources around Matoko. So love to see the efforts. I'm sure there will be many more like it. And again, you know, I think part of it is dependent on the contributions of the ecosystem at large, because again, there's only so much that I think we can do internally, and more minds in the room are definitely better than just ours.
Yeah.
Cool. So next question, what are the plans of the foundation regarding support for other languages that compile to WebAssembly? You know, like creating SDKs essentially for other WASM compatible languages. Is the priority to also support those, or are you guys focusing on Motoko?
Yeah, I would say the answer is kind of similar, right? So obviously we can't like maintain n different languages at the same time. That would be a waste of resource on our side. But of course, all the documentation is there that you would need to build an SDK. I think one thing we need to do on our side is make the SDK itself, like the tooling, the DFX tools and stuff, more modular, so that you could hook in other languages there. But the actual compilers and runtime systems for most of these would have to come from the community as well. And it would be great if we had those, right? I would love to see more languages on the internet computer. Ultimately, I'm like since I co-created WebAssembly, I care about the diversity, right? That's my main goal here. So, but yeah, I mean, we can't work on 10 languages, obviously. So we are focusing on these two. One gives you like a kind of high level thing. One is more like a systems low level thing. And there's much room for something in between or even beyond that. But contributions are welcome, right? We are putting out the CPU, you built the compiler.
Yeah, I completely agree. And we've already seen a lot of great community efforts on this front. So next question, I hope I'm stating this correctly. The person who asked it can clarify in the chat if they want. So the question is, I've heard about this black hole project whereby one can make a whole canister permanent, I think by designating a canister controller over which the creator has no control. Does this in fact make a canister effectively permanent, and are there any loopholes with this?
I assume not. I mean, I would not be the most qualified person to answer that question, but yeah, at least the intention is that there are no loopholes, right? So if you remove like the last controller, then there is nobody who can control it. I guess, I don't know what our government's system could do with it though. I guess there would still be a way in terms of a proposal, like an NNS proposal, to remove it. But that is kind of like an overriding thing for everything, I guess. But,
cool.
Yeah, as an individual, you would not be able to remove it.
Okay, thank you, Andrea. So we still have around like 5 to 7 questions. So I will try to move quickly with this. So first one, how do you take a backup of your data, more specifically restore a canister state to a specific moment in time? Can you do something like that? Or do you have to build it into your design to take snapshots of state variables, possibly from another canister?
Yeah, that's an excellent question. So one of the real shortcomings we have right now with Motoko and the internet computer in general is that we don't have a great debugging story, right? So, and this is related to that. So you can't really look at the state of a canister. You can't really extract it. And extracting it is difficult for, at least in a meaningful way, for the kind of things I mentioned with respect to orthogonal persistence, right? So the heap as is, like if you just look at the bytes, is really only meaningful in combination to a very specific binary that produced it, right? You need to know how it interprets that. So, but there might be abstractions that we could build that allow like in debuggers for native code, for example, that allow you to inspect something. But we have lots of discussions about that, I think, but it's still not entirely clear how you combine these things with the internet computer. So for the time being, you probably have to just build that interface yourself. I mean, you can always do that by providing a method that kind of sends out all the data, right? And you can have a kind of implement some access check on that so that nobody but you can invoke it. But yeah, it's not super elegant, but at least it's a workaround.
Thank you, Andreas. So next question, to check my understanding, all Motoko variables have orthogonal persistence and not just the stable variables, correct?
Right, so everything is persistent. The stable just means that it's also persistent across upgrades, right? So that it even stays alive across upgrades, which other variables don't. That's an important thing to understand because some people are actually confused. So thank you for the question.
Next question, how much does garbage collection cost in terms of cycles?
Well, that's difficult to answer because it totally depends on your like profile, right? So the thing right now, it's still a bit expensive because we can only do like monolithic collections. So that's why we're working hard on providing a generational collector where you only need to look at like newly allocated data. So this is an obvious thing that you want, and that would definitely give like a big boost to the cost of garbage collection. Right now, it's really linear in the size of the live data you have, right? With a generational collector, it's more like linear, at least most of the time linear in the size of newly allocated data and whatever stays live from that. So I can't give you any real numbers. It totally depends on what you're doing and whether you're allocating them. I mean, you can write a program that doesn't allocate anything, right? And you can also, of course, tune your programs to be careful about allocation. So if you understand what constructs do allocation, then you can try to minimize that. But yeah, you can easily write a program that goes crazy on allocation. So I'm not sure how exactly to answer that question, but I would say probably, I mean, just to throw out a random number in like a sanely written random application that does some data, I would say it's maybe like 10-20% maybe of your cycles.
Thank you, Andrea. So 2 very quick questions to close out. Number 1, can Motoko potentially be used on other blockchains in the future, or will it only be meaningful for the internet computer?
That you would have to ask the other blockchain developers that. I mean, I don't think we have any intention of porting it to another blockchain. I don't know how easy it would be. It depends on how well the concepts fit, right? And whether it's like running WebAssembly, which some of them do. But yeah, I don't know.
Yeah, I agree. It's probably up to the other blockchain platforms. And then last question, a fun one to top things off. What is your favorite wine pairing to go with Roquefort cheese?
Oh dear. So actually, not a red wine. I would pick a white wine. Maybe.
Controversial man.
No, it's actually a misconception that red wine always goes best with cheese, especially with strong cheeses like Roquefort. You want more like sweeter wines, so white wines, maybe a very nice sweet Riesling or something. Would be a good pick, but I'm not really a wine expert, I have to say.
Honestly, even for wine experts, I think the correct decision is the one that you like. So I know that we are at time. Thank you so much to the community for your wonderful questions. Thank you, Andreas, for preparing this presentation, and see you guys all at the next community conversation. Bye, everyone.